Hi, this is problem 16 of the AMC 12A. Tetrahedron ABCD has side AB equal to 5, AC3, BC4, BD4, AD3, and CD 12 over 5 root 2. What is the volume of the tetrahedron? Oh boy. So in general, finding the volume of a random arbitrary tetrahedron is quite difficult. So our main strategy here is try to look for some symmetry or some simplification to make this tetrahedron easier than sort of a random arbitrary tetrahedron. And one thing I notice is that we have a 3, 4, 5 right triangle on the face ABC. So let's draw that in to try to get this started. So that's A, B, and C. And let's see, so that's a 3, 4, 5 right triangle. And it also looks like we have the side BD4 and AD3. So that looks like a 3, 4, 5 right triangle as well. So let's draw that in. And it may take more than one attempt here to draw this properly for the purpose of seeing a critical insight. So it's okay if we need to draw this a few more times to get this right. And we also can draw in the side CD, and we're told that this side CD is equal to 12 over 5 root 2. And one thing I like to do when I have these 3, 4, 5 right triangles is to draw in the altitude for the triangle. And it's pretty easy to compute the length of that altitude. It's simply the side lengths 3, 4 divided by the hypotenuse, and that's sort of the equal area rule for determining the altitude of a right triangle. So this altitude is given by 12 over 5. That looks pretty helpful. Let's draw in the other one. Its altitude is also 12 over 5. And now we sort of see a critical insight. We have this triangle formed by the two altitudes and the side CD, and it looks like that triangle is a 1, 1, root 2 right triangle. It's essentially a triangle that looks like that. And that's looks like that's going to be very helpful because right now we have 3 right triangles at this vertex. And the 3 right triangles kind of form what's equivalent to the x, the y, and the z orthogonal coordinates of a three-dimensional object. And that allows us to calculate the volume of this tetrahedron pretty simply now. We can generate the area of this base triangle and then calculate the area of the right tetrahedron and the left tetrahedron and just add them together. So the area of this base triangle now is 1/2 12 over 5 squared, and the altitude for the left tetrahedron we'll call h1, and for the right tetrahedron h2, and we'll just multiply that by h1 and put a factor of 1/3 to calculate the volume. And we'll also have to calculate the right tetrahedron using a similar formula, and just add these two together. So we basically end up with 1/3 times 1/2 12 over 5 squared times h1 plus h2. But we see, of course, that h1 plus h2 is just the length AB, so that's handy. So that works out to 1/3 times 1/2 times 12 squared, 5 squared, times 5. 5's cancel with the square. Looks like we can cancel the 3 times 2 with 24, and that's just equal to 24 over 5, and that is choice C. Anyway, a difficult three-dimensional geometry problem, but if you draw it right, it's pretty easy to solve. So don't be discouraged if you have to draw this thing once or twice or even 3 times to get this right. Anyway, take care. Bye.